Welcome, I'm Dr. Morton. This is the video for Logic Design Chapter 1. I'm also going to do a bit of an introduction in this video. I will cover the high points of Chapter 1, and my goal is to keep these videos short, somewhere in the 15-minute range. Let me first introduce myself. So I have a PhD in electrical engineering, and I am a professor at the University of Texas, San Antonio. Of note, UTSA has just become a Tier 1 institution, so we're now on a par research-wise with all the institutions in the country. I am what's called a professor in practice, so I'm not a tenure-track professor, but rather I'm on contract every 3 years, and I generally mostly just teach several courses, and I do not have a big research activity. I do have some research that I do, and I have applied for some other grants, but my main focus is teaching. I'm also a physician. I spent 30 years as an obstetrician gynecologist, and I'm also a helicopter pilot and a fixed-wing pilot for that matter. I flew helicopters in Vietnam for the Army. I served in the Army for 3 years as an airborne ranger infantry officer, and then separated into the inactive reserves and went back to school. I got my master's at the University of Missouri in electrical engineering, got my PhD, or all but the thesis in electrical engineering, and then I started medical school. And during medical school, I continued to work on my thesis, and as an intern at Washington University in St. Louis, I completed my PhD in electrical engineering. I then finished my internship and 3 more years, completing my residency in OBGYN, and then I served in the Air Force for 21 years as a physician. But during 9 of those years, I was in Wright-Patterson, and I worked in the Aeromedical Research Laboratory, wound up being the chief scientist for about 1.5 years, and then I was also the senior military officer my last couple of years. I then moved to San Antonio, and after a year doing acquisition, I went over to the Brooke Army Medical Center and Wolford Hall Medical Center joint program and became the OBGYN department chair. While I was in that position, I was asked to teach at UTSA, and I taught in the evenings logic design. When I separated from the Air Force, retired in 2004, I then went into private practice, and I practiced in private practice for 9 years, doing gynecology only, so I stopped delivering babies in 2004. I closed my practice in 2013 and went full-time at the University of Missouri as a non-tenure track professor in electrical and computer engineering. I currently teach logic design, which I've taught now for about 20 years. I also teach microprocessors 1, microprocessors 2, and digital systems design. The microprocessor 1 course, which probably is my favorite, we've developed our own project board, which we design the board ourselves. We send the Gerber files to China and get the boards made, and then we stencil solder paste on the boards, and we use a pick and place machine to populate all the surface mount parts. We put it in a reflow oven and bake it, and solder those parts on, and then we give a little kit to the students with the 15 or 16 or so through-hole parts that then they solder on, and then they use that project board for 10 laboratories in their final project. Our latest revision includes 2 processors, a PIC 16F1829 and a ATmega 328, so that they can use one of the processors with the Arduino IDE, and they can use the other with MPLAB X, Microchip's main integrated development environment. And then the 2 processors can talk to each other through the I2C port, or you can connect other connections if you wish, and it gives a much greater range of projects that are doable within a semester because of the Arduino portion. Back to logic design. So what I want to cover, let me shrink this down. I've done the brief introduction already. I want to talk about the definition of digital and the definition of analog. And I want to talk about sort of thermometers as an example. And then we'll also, in this demonstration, I want to try and illustrate the difference between precision and accuracy. And then I'm going to talk a little bit about, is the real world really analog? Because I am a physician, I actually know a fair amount about the human body. And I can tell you that it's really interesting how we're more of a digital machine than you might think. So we'll cover that in a minute. And I'm going to briefly touch on the concept of algorithms, and particularly the difference between a serial and a parallel algorithm and why that's so important and becoming even more important. And finally, we'll talk a little bit about how we manage complexity in logic design. And these are all sort of the introductory targets, and that's what we're going to go over next. Okay, so here's the text, and with each chapter we will have learning objectives, and I want you to look at these. In this one, I want you to understand the distinctions between analog and digital, and some of the advantages of digital over analog currently. And then when I get to the algorithms, I want you to understand the difference between parallel and serial and why that's important. And I also want you to be able to describe the concepts of accuracy and precision. And then we'll talk a little bit about sensors like microphones, sensors, and then displays like video screens, speakers, LEDs, things like that. And we'll talk about how to understand whether they're analog or digital. Okay. So with each chapter, there's a glossary, and if you hover over these definitions, they'll expand and define them. And you should look at these, and then there's actually flashcards at the end so you can review these, because I will ask questions on the test about some of these concepts. All right. So within the text, I spend a good bit of time talking about the definition of digital and analog. And I want to highlight the important points here. First, analog and digital signals both vary over a defined range. And normally that defined range represents the something reasonable. It's the range of the range of values that we deal with. For instance, temperature. If we're talking about, say, atmospheric temperature, then we really deal with, say, something like minus 30 degrees Fahrenheit to maybe something like 120 degrees Fahrenheit. I guess if you get up really high or some of the very cold places, you might go down to minus 40, and there have been occasionally temperatures over 120 on Earth, but that's a pretty functional range. Both our analog signals and our digital signals vary over the same range. So there's defined range, and we allow these signals to vary over this range. But the analog signals vary continuously over this range. So they can theoretically be any value, say between minus 20 and 110 for temperature on the Fahrenheit scale. Whereas a digital signal, we set up some number of bins. We might set up, say, 130 bins, and each bin would represent a temperature in whole degrees. Or we might set up 10 times that, or 1,300 bins, and each bin would represent an integer temperature value with a decimal point of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we have 1,300 bins, we can have more precision. If we only have 130 bins, we have less precision. Now we can only describe the temperature to plus or minus 1 degree. In an analog signal, theoretically, the value could be anywhere in that range For instance, it could be, say, 75 degrees, 0.763. But the problem is that we might not have the ability to measure it that precisely or that accurately. And again, we're going to define those in just a second. So you might think that analog signals are more precise, but that's not true. What's true is that we can make our digital signals as precise as we choose. So we can set up 130 bins over that temperature range, each bin representing a whole degree temperature. So there'd be a bin for minus 20, there'd be a bin for minus 19, there'd be a bin for 0, there'd be a bin for 10 degrees, there'd be a bin for 50 degrees, there'd be a bin for 100 degrees, there'd be a bin for 110 degrees. But there wouldn't be any bins for 50.5 degrees, for instance. We only have 130 bins. If we set up 1,300 bins, now we can have a bin for 50 degrees, 50.0 degrees, 50.1, 50.2, and so forth. We have 10 times the number of bins. If we set up 13,000 bins, then we could have 50.00, 50.01, and 50.02, and 50.03, and so forth, because we'd have a lot more bins. We'd have 13,000 instead of 1,300 or instead of 130. But of course, the more bins we set up, the more expensive our hardware is, because we have to have more memory and more bigger buses and more processing power to handle that. So the limits on digital are arbitrary. On the other hand, because there's a certain amount of noise in the analog world, we don't have the ability to set up precision as much as we want just by having more memory. Because once we take an analog value, say we measure it, maybe we measure it to a tenth of a degree, so maybe 30.1 degrees Fahrenheit. Okay, well, how are we going to store that? And we have to have some sort of analog storage set up. And the problem is that in our analog world, there's always noise. In the digital world, we pretty much can get rid of noise. Once we get the measurement converted to a digital value, we can protect that digital value in a number of ways so that it never gets corrupted. We can add additional bits to it to check to make sure that no errors crept in. We can make multiple copies of it and store them in different places so that if one copy gets corrupted, we can check the other copies and compare them. So we have a lot of things we can do in the digital world to ensure that we preserve our values as precisely as possible. Okay, so that's pretty much what I wanted to say. So in the end, because of noise, our precision in the analog world is severely limited. We normally have to represent things with voltage levels, and when we read a voltage level out of, say, a capacitor or some other device, we're always going to have noise involved with that reading, and there's going to be degradation in those values over time. In the digital world, that's not true. And the reason for that is, in the digital world, we quantize things in such a way that we prevent them from changing values without us knowing about it. Now, we can spend a lot of resources to preserve those values, or we can spend limited resources. And in some cases, if we only have limited resources invested in preserving those values, catastrophic events can occur that would cause our data to get corrupted or lost. I'm sure all of you have had a computer crash, a disk crash, a jump drive stop working, or you've lost a jump drive and you've lost your data. That certainly can happen. But if you make adequate precautions, you can prevent that most of the time. Whereas in the analog world, no matter what you do, there is some corruption that's inherent because of noise. All right. So that covers that. Let me move on. I want to talk about these thermometers. So I have here two thermometers. This one is a standard fever thermometer, and you can see it has a little LED screen here that actually has 4 digits, has a little button to start it, has a little tip down here that senses the temperature. And then here I have a centigrade lab type thermometer. It has a bulb down here at the end that's full of mercury, and then it has a scale. It's pretty hard to see, but you can see that it has graduations along the length of it. And this particular one runs from, I'm looking at it now, let's see, it runs from minus 20 degrees to 110 degrees centigrade. So, but if you look at it, you see the column of mercury, and you have to sort of twist it and see, and you can see here it's right about 30 degrees, maybe just a teeny bit over that. Now, which one of these thermometers do you think is more complicated, more expensive, and which one of these two do you think reads more precisely? Well, if you look at the cost, I probably paid $25 for this lab centigrade thermometer, and I probably paid $10 for this fever thermometer. So the glass thermometer with the mercury column costs more. Now, which one of these two is more complicated? Well, the glass thermometer is just a piece of glass with a channel and a mercury in the end. It's sealed at the top, and it has graduations on it that have been somewhat calibrated so that it's fairly accurate, plus or minus a degree, say. And the same with the sunbeam, but in the case of the sunbeam fever thermometer, it has an analog temperature sensor that then is converted to digital. It has some kind of processor that takes the analog value and calibrates it into the Fahrenheit temperature range. It then has to translate that binary value into a decimal value, and then it has to translate that decimal value into a set of ASCII digits so that when you write it to the little LCD screen, you actually see the numbers on the screen that represent the binary value. And the numbers on the screen are going to be in decimal. Not only that, but we're going to have to control the screen in such a way that we suppress leading zeros, and that when we're below 0 degrees, that we write a minus sign in front. So for instance, if we're at minus 10 degrees, we don't want minus 010.0. We want to write minus 10.0. So we want to suppress that leading zero because there are 4 digits. We want to blank the leading digit because we don't need it. Let's say we have 98 degrees. Well, you would write 98.0. You'd still blank that leading zero. What if you have 100 degrees? Well, now you want to turn on that leading digit and you want to write 100.0. And if it's, say, 100.4, you'd write 100.4. So we have to have something that's going to apply all that logic, the minus signs, blanking the zeros, and all that. And then we want to have a little timer built in so that it'll make a little beep. So we need a little beeper or some kind of a little piezo cell that's going to make a little beep so we know that the thermometer's been in the mouth long enough. And then we have to have a push button. So there's all sorts of hardware built into this thing. And of course we need a plastic case and a battery, and we need to be able to change the battery. So if you think about it, this digital thermometer, although it costs about half of this lab thermometer, is a very complex device. It's not simple. It's very complex. So it totally makes sense that it should be a lot more expensive, but actually it's half the price. Amazing, right? The final point I wanted to make is, if you look at this, you'll notice that we can read this one to the 10th of a degree because it always displays 0.0, 0.1, whatever. This one, we really can't discern 10 different levels between these two marks. Each mark represents 1 degree. You can kind of maybe go half, maybe even a quarter, a half, and 3/4. That's about as good as you're going to read this. So this thermometer, assuming it's calibrated well, is going to be a lot more, it's going to be much more precise and hopefully as accurate or more accurate than this thermometer, because you can't read this thermometer very precisely. Okay, we've covered to some degree the definition of digital versus analog, and we have this knowledge check here. There are knowledge checks throughout the book, and I want you to do these. I think this is a good check to see. For instance, the question is it true that analog signals are not constrained to a range, but digital signals are? Well, actually, that's false. So you select down here false, and then you can submit, and you can see what the answer was when it pops up, hopefully. Yeah, and false is correct. All right. So the next section talks a little bit about Moore's law. And what is true is that the complexity of our digital devices has been, the ability to put transistors on a chip has continued to go up essentially exponentially. We're going to talk about why have we seen almost all of our electronic devices are now digital devices and not analog devices, with perhaps the exception of an analog front end to connect to a sensor. And the reason for that is that digital devices, despite being much more complex than an analog device, are much more capable, flexible. We can reconfigure them oftentimes by just changing out some software or firmware. And they're often much, much cheaper because we can make these very complicated things cheaper than we can simple analog things. But the real world's analog, or is it? Well, let's talk about that. It turns out, and I'll talk about this more as we go on because I'm at 22 minutes now, and we did an introduction too, so I'm going to cheat a little bit on this video, but we're going to finish it up in just a couple of minutes. In the human brain, we have a tremendous number of neurons in the brain with lots and lots of dendritic and axonal connections. And so what we really have is a very massively parallel brain, but each neuronal element is either fully fired or it's not. And so because of that, our brains really work in a very much digital fashion. Our muscles, we have fine motor control in our muscles. I'm an amateur violist. I play the viola. It turns out it takes very fine muscle motion with your left and right hand with the bow and left hand fingering the notes. And you have to get your finger in exactly the right position. You have to change it slightly as you hear the note slightly high or low. And those fine finger motions, how do we control those? Well, it turns out the muscles controlling the fingers in the hand have thousands and thousands of individual motor units. And each motor unit is either fully contracted or fully relaxed. Well, there's a resting tone, but fully contracted or fully at its resting tone. So how do you get these very precise and delicate differences in pressures? And you do that by your brain controlling large numbers of neurons simultaneously and having just a certain number contracting and the rest relaxed to get a precise amount of tension. But again, any individual elements fully on or fully off. So it's really an analog, it's really a digital device. Your muscles are digital devices, essentially. And then let's look at the structure of things. They're made up of discrete atoms, and the discrete atoms are made up of the molecules, and the discrete molecules are made up of discrete atoms, and the atoms are made up of discrete parts, and some of those parts are made up of discrete fundamental parts, and we're not really sure what comes after that. So it's very digital. All right, I want to talk a little bit about precision and accuracy, and then I'm going to talk a little bit about managing complexity and algorithms, and that's going to be it. And I'm going to do that in just the next couple of minutes. So we've already used these terms, but I haven't really defined them. Precision has to do with how accurately you can read something without regard to whether it's the real-world correct answer or not. Accuracy is how close you are to the real-world truth. So this target thing kind of illustrates it. If you have low accuracy and low position, then your shots are all over the target. If you have high accuracy but low precision, then you don't have a very tight cluster, but you're pretty much around the bullseye. Whereas if you have high precision but you're inaccurate, then you have a nice tight cluster, but it's not on the bullseye. And finally, if you have high precision and high accuracy, you have a tight cluster, which is your precision, and it's on the bullseye, which is your how close you are to the real world truth or your accuracy. And that's, of course, what we want to go for. Remember that in the digital world, we have pretty much total control over our precision. It may cost us more money and a more complex device, but we can control precision as much as we want. And that's one of the big differences between digital and analog. In analog, we can't do that. The other big difference is our digital devices are much more complex. And the other difference is that our digital devices, for any given level of complexity, are much, much cheaper than our analog devices. All right. So how do we manage complexity in digital designs? Well, we use layers of abstraction. And we'll talk more about this. We also use some principles of hierarchy, modularity, and regularity. So, for instance, when we make a car, we try and use the same thread design on all our bolts and nuts, although there may be sheet metal screws versus actual bolts. We try and have all these sub-assemblies that can be done independently and then assembled to put the car together on the final assembly line. And for any particular model of car, every single part is identical. So for instance, the right front fender on a Mustang is going to look like the right front body panel on a Mustang is going to look the same for all the Mustangs of that year, except maybe the paint color, obviously. But we're going to have as much regularity as possible. We're going to break it down into as many subsystems as we can, and we're going to have a order of precedence as we design it, so that at some level we don't have to think about some of the lower details. We only have to think about the higher level function. We'll talk about these concepts more. These are very important concepts. At the end of every chapter, if you hit next down here, then there's going to be a quiz, and you can start your quiz. And this quiz is worth figures into your grade. There's a quiz for every chapter, and there are usually 10 questions on the quiz. You only have to get half of them right to get full credit for the quiz. So if you get 50%, you're going to get full credit just like you got 100% on the quiz. If you get 100%, you don't get any more credit. So you just need to get half the questions right. All right, and then we do have these flip cards here where it lets you go through them. Here's analog, and then if you hit flip, it gives you the definition. So you can test yourself and see if you can define these things. And it goes through accuracy, algorithm, quantized, digital, and all these various terms that we had. And you can even shuffle them up if you want. Some of these will appear on tests, but a lot of what's on the test will be problems. All right. I do want to say just a word about algorithms. An algorithm is basically just a logical way to solve a problem. The one requirement of an algorithm is that it has to be realizable. You have to actually be able to do it, and normally that means you have to be able to encode that algorithm in a computer program, for instance. So if you can write the algorithm as a computer program, then that meets the definition of an algorithm. But we have algorithms that are serial, and we have algorithms that are parallel. We can also implement our algorithms with a whole bunch of similar processing elements all working at the same time, or we can implement it by executing step 1, step 2, step 3, step 4. And it turns out that if we want our algorithm to run really fast, then we wanted to be able to do it as much in parallel as possible. We'll talk a lot more about this later. All right, so make sure you read through the chapter, make sure you do the quiz, and there's a homework assignment associated with each chapter as well that will be graded by the TA that you turn in on Blackboard. All right, this concludes Chapter 1 of Logic Design.